So as I said at the outset, this is a fairly straightforward lab tonight, but it does reflect something new that we haven't really talked about before. It's a new type of bonding. It's a bonding called coordinate bonds. And what the bonds we've sort of been dealing with before were either an ionic bond, which was just the attraction of two different charges, or a covalent bond, where you had electrons from one atom and electrons from another atom, and they would come together and be shared between the two of them and form a bond. And that was a very strong chemical bond. A coordinate bond is where only one of the partners in the bond brings electrons. And you see it a lot with metals, where a metal will be coordinated. That's where the term coordinate bond comes from. Coordinated with a lot of either negative charges around it or atoms that have a large number of electrons around them in a very specific shape. And we see this with salts. Salts will have water actually doing the coordination. And we know that oxygen in water has those two lone pairs of electrons. It can actually use those to form coordinate bonds with metal centers. The other is the negative portion of the salt, because we know there's any salt that's going to be a positive charge, at least one positive and at least one negative charge. The positive charges will be interacting with water, the oxygen side, and the negative charges will be interacting with the hydrogens, which are partially positively charged. And so each salt forms these hydrates, although we will find that not all salts are stable hydrates at room temperature. So let's have a look and talk a little bit about more what hydrates are. Oop, there we go. So hydrate is just a molecule that has has water integrated into it. And we know that like hydrogen bonds are pretty strong, right? They can change the boiling point of substances substantially, particularly when we were looking just this week at the difference between the boiling point of methane, which is completely nonpolar. You put an OH group, a hydroxyl group on it, and the boiling point goes up like 250 degrees. So that's a really, really strong interaction. So in this instance, these interactions are so strong that the water is even held on to when it's a solid. So you could boil these things away, boil all the salt away from some of these structures, and they'll still hold on to some of the salt even after all the liquid is gone. So it has water directly into the solid crystalline structure. And these are all unique. Each salt has a very specific number of waters that are associated with it. And what's given here as an example is copper sulfate. And we've used copper sulfate in the lab. Remember, it makes that really, really pretty blue color. And copper sulfate as a hydrate has 5 waters attached to it. Makes this really pretty blue. And then when you drive off the water, it's still slightly blue, but not nearly as much. And we know that the colors come from the electrons moving in the copper. And so the copper is in a different electrical state with the waters and without the waters. And so the color changes. You get a lot more deep blue color when the water's present. And that should also show you that this hydration energy is not the same as a bond. When we heat up water, for instance, We don't break its bonds. It just goes from being a liquid to a gas. The bonds between the hydrogen and the oxygen don't break. And in fact, we could heat it up to like, thousands of degrees, and those bonds aren't going to break. Now, this is a much, much weaker interaction, even though the water is still in the solid. If we just heat it up, we drive off the water, because there's a certain amount of heat involved in this particular interaction. So here we have a balanced reaction. Here we have the hydrate on the left, and then the products on the right. So is this an exothermic or an endothermic reaction?
Exothermic.
Why is that?
Heat was generated.
Because what? Sorry?
Heat was applied.
Heat was applied. Was heat? So is heat, when in an exothermic reaction, is heat absorbed or is heat released?
I thought this was an endothermic.
This is an endothermic reaction. Yeah. When heat is actually a reactant, it's an endothermic reaction, because that heat is going into the reaction. When heat is a product, that's an exothermic reaction, because heat is being released. So this is an endothermic reaction. So going in the opposite direction, making the hydrate, that is an exothermic reaction that releases energy, because this is more stable than these two things separately. So it releases energy. So one of the salts that everyone's familiar with is sodium chloride. So I was interested in finding out whether this can form a hydrate, because we know that the salt we use for baking and sprinkling on our food doesn't have any water in it. It's not a hydrate. Sodium chloride does in fact form a hydrate. It forms a dihydrate. But the temperature needs to be below minus 20 degrees Celsius for it to form. If the temperature is any warmer, it absorbs that heat and releases the water. So at room temperature, we don't see it. You have to cool it down to a very low temperature. And you can see the formation of this. If you have like brine with a high salt content and you lower the temperature to like about minus 30 or so, and sodium chloride will form these really big platey looking crystals that you generally don't see. Usually the sodium chloride crystals we're used to seeing are like really, really small and the same size. And they're all sort of, look like a cube, but you get these really long plates with the hydrate. But the minute you bring it to room temperature, it melts, and you get the water, and you get and then the salt goes into solution. So it does form a hydrate, and pretty much every salt does form a hydrate, but not always they're not all stable at room temperature. So what we're going to do is this reaction specifically, but we're going to be using a different salt. What's the salt we're going to be using?
Epsom salt.
Magnesium.
Magnesium sulfate. That's right. Magnesium sulfate, not copper sulfate. Though I would have liked to use the copper sulfate because it's just so pretty. Magnesium sulfate, if you've seen, obviously you've looked already, right, at your supplies. It's just a white, sort of boring white crystal called Epsom salt. Now, what we're going to do is heat that up, drive off the water, and leave the anhydrous salt. What does that mean? What's the term anhydrous mean? Think of what an means and then hydrous.
like without water?
It's without water, exactly. So an anhydrous salt would be just the magnesium and the sulfate without any salt in the crystals. And that's what we're going to be making. So here's what our pretty blue copper sulfate crystals look like. So on the right, that's the hydrate. So here's the hydrate here. You see the crystals are that bright bright blue color, and they're all pretty much the same size. And then when you drive off the water, you get this sort of cakey looking substance. It's still blue, but not nearly as blue as the other. And you're going to lose a lot of mass. The mass you're going to lose, obviously, is the water. So if copper sulfate is a pentahydrate, what is the magnesium sulfate that we're using? How many waters are in that crystal? Did you look at the label?
7.
7. Excellent. You looked at the label. So what will we call this compound?
Heptahydrate.
Magnesium sulfate heptahydrate, right? And so what we hope to do by heating it up is drive off these 7 molecules of water and just leave the anhydrous magnesium sulfate behind. And then we're going to do calculations to figure out how many molecules of water are there. And so the example that they give here in our lab instructions is if they take a 5-gram sample of copper sulfate and they heat it up. So when they heat it up, they lose some mass. Now, what is that lost mass?
Mass of the water.
It's the mass of the water, right? So that turns into a vapor. So we heat that up, the water leaves as a gas. And so whatever is left over should be just copper sulfate. And the difference between the hydrate and the anhydrous form should be the mass of the water. Now that we have masses of both the water, we have the mass of the water, and we divide that by the mass of the sulfate. If we convert these to moles, well, that's exactly what we're looking for. We want to know what's the molar ratio of water over the salt. That will tell us how many molecules of water are present in each molecule of the salt. So for our particular salt, we're going to be using magnesium sulfate. So we need the mass of magnesium sulfate and we need the mass of water, because we're going to be converting both of those masses into moles and then dividing one against the other. So anhydrous magnesium sulfate is 120.37 grams per mole. And the mass of water, which we should pretty much know by now, is 1802 grams per mole. So each of those masses that we're going to calculate, we will then convert them to moles using the molar mass. And hopefully we get something close to 7. So if you look up magnesium sulfate hydrate, you find out it's a heptahydrate. So that means we should get 7. And last night, my son was helping me out with the experiment, and he got 6.3. So if you can't do better than an 11-year-old, then I don't know what that says about about your scientific skills. So this is, like I said, pretty straightforward experiment. So you get a bag of Epsom salt. So Epsom salt, people have been using Epsom salt for a really long time. Basically, you soak your feet in it. It feels really good on your feet, which is probably something I should be doing. So you get a bag of Epsom salt, 3 aluminum weighing dishes, because we're going to be doing this experiment in triplicate, a can of Sterno, and Sterno is just ethanol in a gel. And it makes this really cool. I think they added some sort of dye to it, so that it makes a pretty color when you burn it. Because generally, when you burn alcohol, you don't get any color at all. If anyone's ever watched Formula One racing, they use methanol as a fuel. And in some of those instances where a driver catches on fire, one of the awful things is you can't see the flames. And so, yeah, that's why in this particular instance, they add something to the ethanol gel so you can actually see it. Now, this thing will burn for about 45 minutes or so, but should give you plenty of time to do your 3 experiments, because we're going to be heating them for 10 minutes each. If you have some left over, you can just put the cap back on the top. Don't push it down, just put the cap on the top and let the fire go out by itself. And actually a little vacuum will be created. It will pull the top back on. So we need our balance, and we need some forceps, because we do not want to be touching these aluminum weighing dishes after we've been heating them for 10 minutes. They're really, really hot. So yeah, oven mitt, tongs, something like that. And you're going to want to put this wire stand on something that isn't going to burn. This is going to get hot. The Sterno can is going to get hot. So you don't want to have like paper or paper towels underneath it. You want to have something like, it would be a good time to have like a cookie tray or something like that. Okay. So we want around 0.5 gram between 0.3 and 0.8 grams. So we're going to weigh the dish. So the dish is going to be around, I don't know, let's say it's like 1.30 grams. So what you're going to want, we're not going to tear. Usually in this sort of situation, what we would do is we would weigh something on the dish and then tear it back to 0 and then weigh whatever we want. This time we're not going to be doing that, because at the end of the experiment, we're not going to be removing the anhydrous salt. It's still going to be in the pan. So we want to make sure that we get the mass of the pan plus the salt. So if it's around like 1.3, we're going to want to add salt till we get to somewhere between 1.6 and like 2.1 grams. Then when you're doing your calculations, when we subtract the mass of the dish from the original salt, that's going to be the mass of our hydrate. Then we're going to heat it for 10 minutes. And then the mass of it after the heating, again, after we subtract the mass of the dish, that will be the mass of our magnesium sulfate. And the difference between the original mass and the mass after heating, so the delta mass, the difference will be the mass of the water. So we'll have mass of the water, mass of the anhydrous salt, convert them both to moles, and we're done. So fairly straightforward experiment. So this is our setup here. So you're going to want to label the dishes 1, 2, and 3, and as you're you're heating the first one, you can start weighing out the second and the third. So you'll have those things ready to go. So heat them each for like 10 minutes and then let them cool. Last night I noticed that after we waited after about let it cool down for about 3 minutes. And then I waited again about 5 minutes later and the mass had changed slightly. So you may want to wait for like a good 10 minutes before you weigh the dishes again, because there still could be some evaporation going on. So yeah, I noticed I mean, it wasn't a big difference. Notice a difference of about 0.01 grams less with a little more time. And the more accurate you can get the calculations, the better your results are going to be. And then the calculation, like I said, pretty straightforward. So we want the mass of the dish by itself, the mass of the aluminum dish plus the salt, and then the difference will be just the hydrate. So that's the mass of your hydrate. After heating, then subtract the mass of the aluminum dish again. That is the mass of the magnesium sulfate. The difference between the mass of the dish plus the hydrate and the mass of the dish plus the magnesium after you heat it, that's going to be your mass of the water. And then so this is going to be in grams, this is going to be in grams. We'll convert them both to moles, and then you want the ratio of water over the magnesium sulfate. So pretty straightforward. So any questions before we get started? We're good to go. Okay. Yeah, so this really should only take us about an hour or so, because it's pretty short. And basically, you're going to want to be careful, like I said, because we're playing with fire, like in actuality. So I'll give everyone 5 minutes to get all their stuff together, and then we'll meet up and go through it, okay? All right, so 5 minutes, so let's say 10 to 8, we'll get started. So I will see you in a minute.
Professor, I think you're muted.
Yeah, I think you're muted. because I can't hear anything.
Thank you. Oh my God, yes. I was wondering. So I weighed my dish. It's about 1.29 grams. So I'm going to want to add Epsom salt to around 2 grams. If I add way too much, then I'm not going to be able to lose enough mass in that 10 minutes to really get an accurate estimation. If I use too little, then my difference will be so small that my error will be large. So the sweet spot is like around 0.5 gram or so, more or less. That is too much. Yeah, some of these crystals are really big, so. There we go. So 1.94.
So you wanted it at least at 2 grams then?
A total.
Oh,
So
okay.
whatever, I don't know what the mass of your dish is going to be. I can only speak for mine. But it's probably around 1.3 grams. Am I right? Everyone's got about the same?
Yeah. Because the mass of the total for me was 1.70 for one of them, and then 1.91 for the other.
Wait, what?
The mass of the dish and the Epsom salt.
Is 1.7?
0.
Really?
Because they said that you want to measure between 0.3 and 0.8
That's the amount of,
of the salt.
yes. All right, so your total is 1.7.
Yeah.
Okay.
Is that an issue?
Well, is it between 0.3 and 0.8 grams of salt?
Yeah.
Well, then you're good.
Okay. Just making sure.
And my mass keeps changing. 1.92. Maybe I just have a crappy balance here. Yeah, you can see this. I don't know if you can hear it, but it makes this crackling sound.
It does for me too, actually.
You want to spread the crystals out so that kind of sort of evenly distributed. And then just pop that on the top. And what you'll notice is that they start to sizzle. It looks like they're melting, but actually what's happening is that as the salt is being released from the crystal, the salt then dissolves in the liquid water. And then when the water turns into a gas, then it's gone. So first the salt dissolves, and then it's left as a anhydrous. And you can use, if you have a pair of metal like I have, you can sort of move them around. You'll notice that after a while, if you get like a single crystal by itself, it gets really small and almost turns into like a brown color. But you do have to be careful because sometimes you'll get like a popcorn effect. And when the water leaves, sometimes it'll just might pop right out of the dish. Oh, I forgot to set a timer. Yeah, so you want 10 minutes. Like I said, while this is heating, you don't want to turn your back on it or anything. You can label the next 2 dishes and add your salt and get the mass, so they'll be ready to go.
Did you want the flame to, like after we're done with like the first one, did you want the flame to still be on?
Yeah, you just take the first one off, throw the second one on.
Okay. my my sister she was asking if you're from Atlanta, and I said no, you're
No,
Canadian, and she was like, oh, then why is he wearing that shirt?
I like minor league baseball teams.
Oh,
This was a minor league baseball team, which changed its name for more or less obvious reasons.
oh, yeah, I can see why.
Yeah. Yeah, you can call them the Braves and that's fine, but you make fun of Crackers, someone's going to get upset.
And I just want to make sure, so we heat it for 10 minutes, and then how long do you want it to cool before we weigh it? It was like another 10 minutes?
Yeah, 5 to 10 minutes.
Okay.
Yeah, I just noticed that my mass changed after time, but now I'm beginning to wonder if it's just the crappy balance I have. Yeah, and the other reason we don't really take the product out is that you can see it's sort of sticking to the pan. So trying to scrape all that out would be tricky. So it's just much easier just to weigh the whole thing.
I saw what you had for like, the things that we may need to bring back for the chemistry kits.
Mhm.
What do we do with all the other items?
You can toss them, you can keep them, you can, yeah, because the rest of it is just stuff that isn't dangerous.
Oh,
Pretty
okay.
much the only stuff they want back is like hazardous material, like concentrated acid, concentrated base. The phenolphthalein, it's kind of, that could make you sick.
Because I was just thinking, like, if we don't have use for them, can we just bring them all back to them?
Well,
Maybe
contact, you'd have their contact information, so
okay.
you can ask them directly. I don't think they want them,
Oh, okay. Because I thought maybe
which
you guys could
surprises
reuse
me
it.
because I figured we could use that.
Yeah, that's what I was thinking too.
Because
Because I mean, like
I don't
the
know what
glass
anyone else is going
tubes.
to do with this.
Yeah. Does that just have to do with COVID, or is it just like, I don't know. I mean, I don't know why you
No,
guys
I don't
wouldn't be
think
able to
so.
reuse it.
I don't know. Just, yeah, look, ask them.
Okay.
Yeah, they made the policy, not me. I would have taken all of the stuff back, but maybe they just don't have room for it. That could be the reason.
And sorry, I just want to make sure, when is our last lab? Because,
I don't know. I need to look at the schedule.
okay.
As well, the lab next week, not the week after. And I think we'll probably just do one more. So I think we're just going to do 2 more.
Okay.
Yeah, I like watching the gel. Anyone notice the gel's kind of like pulsating, like it's alive? Maybe that's just mine. All right, got 2 more minutes. Yes, you should have the second and third weighed up and ready to go. Then you can just do this pretty quickly. And like I said, the calculations are pretty straightforward. So another difference between the hydrated salts and the anhydrous salts is that, coming from someone who made a lot of solutions in the lab, we always preferred the hydrated salt because that would go into solution really fast. And the anhydrous would take forever. It's almost like you have to force them to take up water again after they're anhydrous. But when they're nice and hydrated, these nice big fat crystals, they go into solution really easy.
I'm just wondering, are Epsom salts, I know that they're used for bath. Are they the same as bath salts, or are they completely different in terms of chemically speaking?
You mean bath salts, the drug?
Yeah, I always thought bath salts were, like salts that you use for the bath. And then you just ingest them, but
No. No, they were called that so people, because it was a new drug, and so there was no law against it, because if you can't define what it is, you can't arrest someone for having it.
oh,
And I guess they had big crystals, and so they just called them bath salts.
oh, I see.
But it has absolutely nothing to do with this. That was back in the designer drug days.
I see.
Or basically take, something like amphetamine, put a methyl group on it. Now it's methylamphetamine. Now it's meth, so it's, it's different. But meth has a much longer history than that, actually.
Yeah, I heard, what was it? And amphetamines, I believe, used to be used as a weight loss drug
Mm-hmm.
before they found out how bad the effects were.
It's also the drugs that the Japanese gave to their kamikaze pilots.
Oh, wow.
German army used a lot of methamphetamine as well. So it's been around for a really long time. All right, so it's like 12 minutes. So I'm going to take this off and just let it cool. Now this thing's still burning. So what I'm going to do is just put the top on. I'm not going to push it down. Just put the top on and just let the lack of oxygen just put the flame out. And then just not touch it because it's pretty hot. Maybe the surface isn't flat. Maybe that's why I'm getting weird readings. Yeah, so needless to say, you don't want to, like, be inhaling the fumes off of this or be breathing on it or anything like that. Just let it sit to the side for a few minutes and then cool back down. It is metal, so it will cool fairly quickly. Okay. Yeah, my mass is going down slightly. You want to just let it sit on the balance for a minute, because mine is still changing. And again, I don't know if that's because it's actually losing water still, or I don't have a balanced location. Take it off, re-tear it, and see what happens. Oh, interesting. Okay. All right. Finally settled on a mass there. All right, so I am going to go back to the table and do my calculations. Not muted. Okay. So I need my notebook with all the data on it. So the mass of my dish, fatter text than that, 1.29 grams. .92 grams was dish plus hydrate. So the mass of my hydrate 0.63 grams. So you can see we're basically going to be stuck with two significant digits for this particular lab. Now, dish plus the anhydrous salt was 1.60 grams. So my anhydrous salt is 1.60 minus 1.29, 0.31 grams. Go away. Okay. So what is the mass of the water? Well, that would be the mass of the hydrate minus the mass of the salt. That's 0.32 grams of water. So now I've got that's pretty much all the data I need to collect. So I have my mass of water, I have my mass of salt, pretty much almost the same. So now I have a mass to mass ratio, but that's not really what I want. What I want is a molar ratio So all I have to do to get that, to convert that into moles, convert that into moles. So that's what I'm going to do next. So that's my water. So I want moles. It's going to be 0.017758. Now remember, don't worry about significant digits at this point. And notice a lot of people on the test were rounding their numbers in the middle of calculations. I saw that a lot with the I think it was question 3. You're trying to calculate pH. People figured out what the concentration of H plus was, and then they rounded it down to 2 numbers before taking. Actually, none of you actually took the log. I don't think anyone did that correctly. But you rounded the number before you got the log of it. And that's not what you want to do. You want to keep as many digits as you can that will give you additional precision, and then round at the end. So at the end, we're going to want 2 significant digits. But now I can use however many digits I want right now because I'm in the middle of a calculation. So I want to use at least 3. I want to use more than the number of significant digits I have. That's my moles of water. Moles of water. As far as my salt goes, so my anhydrous salt is 0.31 grams of magnesium sulfate. How many moles is that? 1 mole of magnesium sulfate is 120.37 grams. I believe that's, yeah, 120. So I get rid of my grams, Left with moles. That is 0.00. Remember, we're dealing with moles. Remember, moles is a large amount. So we deal with these really small numbers. So it's important to keep your zeros in line. 25754 moles of magnesium. I should have fewer moles of magnesium. Even if the mass is the same, I should have far fewer moles of magnesium because the moles are so much bigger. So let's see what we get. So then we just get the ratio. So 0.0025754. Oops, I want to go the other way. I want to put my moles of water on the top. So 0.017758. So I've got water on top, magnesium on the bottom. See what that ratio is. Oh, this is sweet. So that ratio is 6.895 to 1. So that's the ratio. So remember, we need to round this to 2 digits. So those are my 2 significant digits. And since there's a 9 next to the 8, we round that up. So my final answer will be 6.9 moles of water for every 1 magnesium sulfate. And I'd say that's pretty close to 7. So I have to rub this in my son's face, so I got a better answer than his. Actually, I think I just heated it for 2 minutes longer. Yeah, so you see, it's pretty straightforward, and we want to get, obviously you're going to want to get close to 7. What are the questions on the, actually there's only one question. It's a really easy report too. One of the questions on the report is like basically errors. It's like, what would you expect if your number was too small? Let's say you only got 4 moles of water for every 1 of magnesium. What would be the errors associated with that? If you got too high a number, let's say you got 10 moles of water for every 1 of magnesium sulfate, what would be the errors involved in that? So you need to think about what possible errors you could have come across during the experiment, and what effect would they have? Like, what would happen if one of the crystals just popped out and out of the dish? What would that do to the ratio? Or if you didn't heat it long enough, what would that do to the ratio? Or if you didn't zero the balance properly, what would that do to the ratio? So all those things, think about what effect that would have.